Welcome to the Building Science Podcast.
Welcome to the Building Science Podcast.
Bringing the human factor to construction, design, and architecture. Brought to you by Positive Energy in Austin, Texas. Hey everyone, and welcome back to the Building Science Podcast. I'm your producer, Michael.
Hello, and I'm Christoph Irwin, your host and speaker for today.
Today we're going to be talking about air controllers. We talked previously about bulk water and kind of introduced this series of podcast episodes that are focused on the building envelope and how the enclosure is mitigating heat, air, and moisture. So with that, I'll turn it over to Christoph to give you the ins and outs of what happens to air.
Air. Air is everywhere. Our houses and buildings are sitting in a sea of air. In fact, to think accurately, you are scuttling around like a lobster at the bottom of the ocean. You are scuttling around on the surface of the earth under this massive sea of air. And just 1 square foot of air has about 15 pounds of force pressing on it. So it's a lot. It's very heavy. We lose sight of that. It's important to keep perspective when you're thinking about air. Let's talk about, for instance, just to give you a kind of a sense of things. Keep in mind, my goal is to give you understanding and a sense of things rather than to give you a bunch of numbers to memorize. When we're talking about moving air around a house, let's use for an example a 3-ton air conditioner set at 360 cubic feet per minute per ton. Operating on the average day here in Austin, which is around 9 hours a day of operation, that is going to move more than 40,000 pounds of air that one day.
That's a lot of air.
That's a lot of air. So you got that right. 40,000 pounds of air, 20 tons of air moving through one small 3-ton air handler on an average day here in Austin. So don't trivialize that, right? These devices that move air, like your dryer, your range hood, your air conditioner, your furnace, these are very powerful fans. They're pumps. They are pumping massive amounts of a relatively heavy fluid, the air, in, around, and through your house. And if you don't think air can cause unintended consequences, you're wrong. It can. To put your finger on one of the most complex features of building physics or building science, it is the complex interconnections of air and air moving under natural convection, forced convection, in, around, through the building assemblies and components. It's a big deal. A tornado, right? It's just air. It's very powerful. So I guess that's the caveat there. When you're thinking about the air control layer and when you're thinking about air distribution and the devices that move air in your home, these are powerful forces and you need to take them seriously. So having a good air control layer is a big deal. So let's look at that for a minute. Air control layer, it's self-definitional right there. It's controlling the movement of air from outside to in. So before we talk about the control layer itself, we were talking in an earlier episode in this series on 3 factors that create a problem, that create a leak, right? There's something to leak, there's a driving force, and there's an opening. So most of the discussion on an air control layer seems to center around this idea of openings and how to deal with openings. Briefly, I want to put in perspective for you the driving forces, right? So it's a given. You're sitting in this sea of air, so there's air, there's something to leak. Now the driving forces in a house, I guess there's 2 main ones, right? There's appliances, like I said, the dryer, but that's relatively small compared to the air handler. The fan, it's either in your furnace or in your heat pump. It's inside your building. That can create on the order of 250 pascals of pressure difference. A pascal is a Newton per square meter. It's a relatively small amount of pressure. Someone used the metaphor of like a $50 sitting in the palm of your hand, or a butter patty. It turned out to be exactly the right one. But a small weight in the center of your hand, that's about a Pascal of pressure. So 250 of those would be about what the most pressure difference that your typical air handler can handle. Typical in a residential, even commercial context can handle. Compare that to wind. Typical wind depends on the size of the building and the height of the building and how exposed it is, if it's on a hill, if it's in a downtown neighborhood. But you can, instead of being 250 pascals, you can be 1,000 or even 2,000 pascals of pressure difference from inside to outside created by weather. So that's a big deal, right? These air pressure differences, they create high pressure areas, they create low pressure areas. Therefore, they create uphill, they create downhill, and air is going to move from one to the other. A typical situation, let's say it's even a windless day inside a house, the dominant air movement force is going to be a pressure difference created by the mechanical system. It is very, very common. Those of you listening to this podcast have probably heard about the dangers of supply side dominated duct leakage and its ability to depressurize a house and to draw air from outside to in. Well, you're not going to be done hearing about it because we're not done doing it. We put ducts in houses in a process-based approach, and even the testing has become a process-based testing where it seems that the testing shall not slow down the process or schedule. But that's another topic. So air conditioners created downhill from inside to out or outside to in, depending on how well the duct sealing was occurred. Okay, so that's the introduction. There's always going to be some sort of driving force, whether it's wind, whether it's your mechanical system, your dryer, your vent hood, your bath fan. There's almost always going to be some driving force. Oh, I missed one. There's going to be stack effects and reverse stack effects. The air temperature inside the house relative to outside is going to cause the air to have a pressure difference relative to the outside. Typical one here in Austin in the summer is hot air rises, right? Because that's the cliche, but that's not at all accurate. Hot air is less dense and floats on cold air. So hot air goes to the top, pressurizing. Cold air, you could say, which is just non-hot air, it is more dense and it falls. Just to give you a sense of that, right? Just simple air density. I mean, maybe this will help, right? This is something that's stuck with me for years now. Let's say you have one air molecule. Well, obviously it has a certain mass, right? Certain molar weight, this nitrogen molecule. And its density is going to be its mass divided by how much volume and space it takes. Well, we know that heat is the vibration, is a measure, simply a measure of molecular vibration. So if you take a molecule that is standing still, well, actually that would be at absolute zero, so unachievable anywhere in the universe. In fact, the closer we get to absolute zero is quite an interesting saga to talk about, maybe on a future episode. But so if you have a molecule and it's vibrating, let's say it's vibrating kind of slowly, so it's going wonk 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 back and forth. And over the course of time, the excursion from left to right, up and down, back and forth, would trace out a sphere of a certain size. So now you add heat to that molecule. Now it's going waka 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 even faster. You add more heat. It's really going, shooting around. What's happening in each of those situations is it's accelerating, getting to the end of an excursion, decelerating, moving back the other direction. It's vibrating, right? It's vibrating around a center. So a very hot air molecule occupies, like, let's say a basketball size volume of air, and a cold air molecule would occupy like a ping pong ball of volume in space. So if you take the same weight and you put it into a ping pong ball or a basketball size, the one that's basketball size is going to be less dense. It's going to float. It's going to go up. So that's just a very kind of a basic understanding of how molecular vibration, which is heat. Anytime you say a temperature, what you're talking about is measure of heat and measure of molecular vibration, whether it's a solid or a fluid like air. or a true gas. So hot air becomes less dense, floats on cold air. That was a little excursion. So now we're going to talk about holes, right? Are there holes in the control layer? Are there holes? The answer is absolutely and yes. We talked earlier that there are some that we're fine with, right? We want our windows to open and we want to be able to move through our doors. So those are intentional holes. Those of us in the building science industry are not against intentional holes. There becomes a limit, right? So talking about holes that we don't want, and there are lots of those. Let's go through a list of some of the common ones. A lot of these come out of the Energy Star version 3 thermal bypass checklist. The biggest one is probably the ceiling of any average house. If you have an attic above a ceiling, whether it's a 1-story or up on your 2nd floor, every ceiling fixture, every smoke detector, any penetration through that ceiling creates an air control layer problem between the inside and the outside of the house. Not to mention that, well, I'm going to mention it. From a health perspective, the air that moves from the attic down into the house through that hole, it's filled with things that we really don't want to be breathing. The particulate matter there has the ultrafine particles of glass, if we have fiberglass insulation, and it's got pulverized, desiccated bug parts, critter parts, bug poop, critter poop. All that stuff is really high on our allergen potency. And not to mention it's got heat, and if you're in a humid climate, moisture, all of which are things we don't want to let into the house. That's one example of sort of an unintended consequence of that creates holes between the inside and the outside. There's a number of them, and what you want to do is you want to particularly prioritize ones like that ceiling hole where the hole is occurring in a format or a configuration that allows for vertical airflow, because we talked about that air becomes buoyant or less buoyant as it changes temperature. As you go through a diurnal cycle over the course of a day, air is changing temperature that whole time. So there's constant buoyant, or what's called stack effect or reverse stack effect forces moving air up and down. So this means you kind of prioritize. The same thing happens on thermal control layers, right? You prioritize the floor and the roof, and same thing on air control. You really prioritize the vertical surfaces when it comes to looking for air leaks from inside to out along those planes. So other ones that happen a lot are chases, vertical chases for air conditioning ducts, for example, or for a chimney flue or a water pipe. The attic access needs to be sealed. The way roofs connects to houses can allow air leaks directly from the house, the wall out into the roof, and it might not be sealed. So there's a lot to think about when it comes to air leaks, but really it comes down to, in terms of the construction process, the time that air sealing is occurring is after the framing, after the sheathing. Some product has been chosen to be the air control layer. And we talked about this because that same product, or in the bulk water control layer about rain, that same product is very likely controlling bulk water flow, preventing that from getting into the house. So when it comes to air, let's think about it this way. If you're going to put on a non-woven house wrap on your outside of your sheathing, so let's say you're going to put Tyvek drain wrap out there. You tape the seams on the Tyvek using that manufacturer's tape, because that tape Tyvek is your air control layer. You arrange that Tyvek shingle fashion overlapped from bottom to top because that Tyvek is your rain control layer. So that's an example there. And then you tie it and make sure that every opening is tied in so that air sealing has been thought of. This is one of the reasons why fluid applied air barriers are coming on so strong. The Air Barrier Association of America offers certification and excellent testing for that. And we offer those services at Positive Energy. There's a number of people out there doing that. Air control layer testing will be done before your house is done, right? It's often too late, and it's a pretty unfortunate to get to the end of a house and find out that the blower door score fails. There's not as much you can do at that point. And depending on if you're just going under IECC code, that's a relatively low bar to jump over. I mean, it gets higher north of here. But right in Austin, we're only under an ACH at 50 pascals, air changes per hour at 50 pascals of 5. So between modern materials, sheet goods on the outside, and then the big one is the sheetrock inside the house, which is taped and floated to the ceiling and the floor. You add all that up, it's going to be pretty easy to pass code. But code is just code. It's the minimum, as we know. It's the what is it? The worst house you're legally allowed to build. If you're going toward the Army Corps of Engineer number or the Canadian specs or the passive house specs for air leakage, you really got to pay attention to all the small holes, and everything should be gasketed and sealed with foams and caulks and tested with smoke, tested prior to assembly. What we're up against is this process-based approach to delivering a house, which we all see it. And all those of us in the construction industry, we see it. First, we go to great lengths to frame and sheathe our building, and then what happens? All the trades come in, right? Electricians, plumbers, air conditioning contractors, and they cut everything full of holes. I mean, they have to, right? They have to get their services through our building enclosure, which is in the way. So our building enclosure details need to take that into account and be well thought out to take care of that. Air control layers have some characteristics, right? You can use Tyvek as an air control layer all on its own. You shouldn't, though. What you want is something with rigidity. You don't want it to be ballooning out and billowing in behind the walls each time the air pressure changes or each time the wind blows. So it's much better to have some sort of plywood or OSB or rigid insulation. Sheet metal is a good air barrier. So sheet goods for air barriers might work temporarily, but long-term, they're not a good idea. This air barrier concept, I'm finding that I have to kind of separate it artificially during this podcast right now because it is tied directly into thermal control layers. We don't want air moving through our insulation, so this means that where we do our air control layer becomes very important. The big takeaway is depending on the size of the gap and depending on the materials, the temperature difference, and the moisture tolerance, the moisture exposure you expect it to have, those are going to drive your decision on what type of sealant to use. Latex, butyl, silicone, and pure polyurethane. Separate from this, maybe we'll talk about a different time, but you can look into each one of those. They have different properties, and they each will have their own best application. As far as the holes that you'll be sealing with that caulk, there are lots of them. Right? There's the connection between the house and the garage. Very important that not be air permeable, right? Whenever you park your car, the hot flue gases exit the car exhaust system and they're in your garage. So if they're in your garage and your home is depressurized because you have duct leakage, well, it's not unusual at all to have the garage air entering the house. And if you've got your mower and some paint cans and gas cans in the garage, that's even worse. And this is not just some crazy happens once a million times in a million homes scenario. This is very, very common, and it's so common that we don't think about it. We don't even notice it as a potential problem. You just look at the way the framing, if you can see your house, if you're a framer, a builder, or a buyer of a new home that's being framed, look at the separation between the garage and the house. If the garage is handled just like another room with continuous joists with no blocking on the ceiling level, that's a problem. That's definitely a problem. You need blocking at the rim and band joists around the garage, and then you need sealing to happen there. We mentioned chases that go vertically for air conditioning ducts and for furnace flues. Those are a big deal. Those are vertical openings from one space to another, so there's going to be a lot of natural forces moving air up and down through those. We also have the standard industry response to that is they're going to wedge something fluffy into that hole to prevent air movement, and that doesn't work. Mm-hmm. Fluffy things filter air. They don't stop air. So if you look under your bathtub at let's say you can see through your garage ceiling and you got a bathtub up there, there's going to be a big cutout in the floor where they've put your P-trap in for your tub, and that needs to be blocked, and that needs to be sealed with foam or blocked carefully and caulked. Even today, I still see a lot of installations where just a piece of fiberglass bat is wedged in there. So visually it looks finished, I guess. It doesn't work. Same things for all the plumbing penetrations, all the interior to exterior electrical penetrations. They all need to be foamed or caulked. We mentioned the ceiling plane. That's a really big one. So those are the areas where air gets in and out. And then there's, of course, the the intentional pathways we make for air inside the house, which are your ducts. And it's really not well thought of, but from an air control layer perspective, if I'm being careful on the outside of the house to make sure that I've got on the house wrap or the peel and stick or the fluid applied, I really need to be careful inside the ducts, because the inside of the ducts is the inside of your house. And the inside of the ducts is often separating the attic space from the house space. So you really want to make sure those two areas are not communicating. You want to make sure the attic air is not getting into the house and vice versa. And that brings up testing, right? So I know that many of you that are listening know that we are on a mission to make testing high quality, careful, meaningful, and lead to good outcomes, not just a happy, smooth process where testing doesn't slow things down. If testing needs to slow things down, it should slow things down. It's the one time when you're working on the house where you have a chance to make it right. There are many different ways. I can think of at least 7 different ways to measure airflow, depending on the configuration. And I'm not going to go through all of them, but I want you to know that a good testing company is worth their weight in gold. They're protecting your reputation, they're protecting your clients' health and comfort, and they're protecting your peace of mind. So when you're shopping for testing companies, think about the quality of the skills of the actual person inside the house, right? Imagine you go to your doctor and the person that's measuring your blood pressure, they're just interested in getting that cuff on your arm, getting the number off of a piece of paper and moving on to the next patient. That's their motivation. That's what they're paid for. That's a really bad idea, right? So if they've got to test 100 patients that day and you get a bad score, they might or might not tell you. It's not unusual for us to go into reasonably new homes and find compliance paperwork that's passing and measure half or double, depending on which way you want to go, failure in those same areas for duct leakage and enclosure leakage. So the big ones for testing air control layer, the biggest one is your blower door test. And that's a test where you use a calibrated fan to either pressurize or depressurize your house. And what that fan does is it maintains a constant pressure from inside to out. And to maintain a constant pressure, it's got to be moving the same amount of air through the fan as is leaking in at that pressure difference through all the holes and gaps in your house. Very simple point, but it's elusive too. I'm going to say it again. So you have a fan that's calibrated, and that just means when it's on and it knows how fast it's spinning, or you can measure how fast it's spinning with the device, and therefore you can know how much air it's moving. So it's moving a certain amount of air, and you know what that is. It's also keeping the pressure difference between the inside of the house and the outside of the house constant. So that means that any air leaking in through the house based on that pressure difference, or leaking out of the house based on that pressure difference, is the same amount of air as moving through the fan.
Another way to think about it would be that all sides of the building are under the same, let's say it's a 20-mile-an-hour wind on every side of the building.
Right.
What that allows you to do is find where all the leakage might be happening, and you're able to actually measure that because it's constant, right?
Right. That's exactly right. You can use a smoke pencil or a smoke machine or an infrared camera. They're all great ways to, depending on the temperature difference between inside and out on the infrared camera, they're great ways to understand the difference there. Great ways to understand where the leakage is occurring. When you're doing these tests, you're looking for leaks, and you're looking for leaks that are almost always found in the same places, right? We've talked about most of them already, and these areas just need some sealant on them, or they need to be done right. And I just want to make sure people understand that, like in our climate zone here, we have a ACH, an air changes per hour number of 5 at 50 pascals. So that's allowed by code. And briefly, just to give you air changes per hour. So if you take the volume of your house, so let's say you have a 2,000 square foot house with 9-foot ceilings. 2,000 times 9 is 18,000. You have 18,000 cubic feet of air inside the house. That's your volume. If you divide that by 60 minutes in an hour, now you're going to have a number that's cubic feet per minute. So that's going to be the number of cubic feet per minute leaking in and out of the house. And it's going to be a big number. But it's under test conditions. It's under these test conditions of 50 pascals, which is actually what you were commenting on, Michael. That's roughly a 20-mile-an-hour wind blowing on all sides of the house in terms of the velocity there. And what I wanted to point out was when you have an ACH 50 of 5 on an average size house, let's use a 2,000 square foot house again with 9-foot ceilings, you're allowed something like close to 100 square inches of leakage. That's not a particularly small hole, right? You can almost stick your head through that hole. So that's what you're allowed. And this is uncontrolled leakage year-round. By the way, when the weather's at its worst, when it's strong winter storms, that's almost always when the pressure differences are strongest. So that's when the holes are the worst problem. So that's air leakage through the enclosure or the envelope. It's measured with the blower door. The next most important test, it's also air leakage through the enclosure if your ducts are in an unconditioned space, and that's your duct leakage test. Now this one, the easy way to remember a duct leakage test is to think about someone handing you a balloon to blow up. And right before they handed you the balloon, they took a pair of scissors and they snipped off a small hole in the balloon. So you take a deep breath, you put the balloon to your lips and you start to blow, and you're like, you hand it right back and you say, this balloon's got a hole in it. I can't blow it up. So what you did to know that was you didn't feel what? You didn't feel back pressure in your mouth. You started to blow the balloon and there was no back pressure in your mouth. That's the simple basis for a duct leakage test. The duct leakage test is accomplished by attaching a fan that pressurizes or depressurizes your duct system. But first, you've configured your duct system so that there's no holes. It shouldn't be leaking at all, right? There's no intentional holes. You've taken all the return grills, all the supply registers, and you've sealed them so that there's no leakage through those. So any leakage that's experienced by that fan, right? And basically the fan, let's say it's pressurizing. It blows into your duct system and it feels the back pressure and it measures the back pressure. So duct system is very leaky, it's not going to get much back pressure. It's going to be a high leakage number, low back pressure number. If your duct system is very tight, it blows in and right away feels that back pressure. So that's what it's recording. It's a really important test, and it's a really important test to be done carefully and right. There are several other diagnostic tests that can become useful when you're going on a job site. These are called zonal pressure diagnostics. They typically go under the term ZPD. And it's measuring things like the relative connection in terms of air control between the house and the garage, or the house and the attic, or the inside of a wall to the outside of a wall, or the crawl space to the house. If you've got a known pressure difference from your house to the outside, then you can measure the pressure difference of your attic, garage, or crawl space to the outside. It's very easy to understand, well, at this time, that crawl space is actually inside my house. Or if it's done properly, it'll be outside your house, let's say. It depends on how it's been designed. And as you'll learn or know, there are two main ways to design crawl spaces. They can be inside or outside the house. The last test that's typically done is exactly that, is measuring the pressure difference from inside to outside. And that one is done with the air conditioner running, and you're trying to determine with that whether it's pressurizing or depressurizing. And that's talking about where the main leaks are. Are they on the supply side or the return side of the house? Okay, so there's a lot more to say about the relationship between air control and thermal control layers. I've actually kind of reined myself in the last few sentences here, trying not to talk about things that relate to the combination of thermal control and air control. We'll leave that for the thermal control podcast. But to summarize, on the air side, there's always something to leak. There's almost always holes and driving forces. And your job as a builder, designer, is to really be careful on the unintentional holes side and to seal them carefully. And often this is supported, I shouldn't say often, always this is supported by careful testing during the process of putting up your air control layer. So we'll get back next time. We're talking about vapor control and then thermal control after that. And we look forward to having your ears listen at that time.
And that's exactly when you're going to have to tune back in to hear what else we have to say. Thanks so much for listening.